So now let's talk about these in more detail. So we'll start out with instruction fetch. What does instruction fetch do? Well, the first thing it does is it keeps track of the current instruction address. And it does this in the program counter register. So here's the program counter register. Then it needs to increment the program counter by 4 on each cycle. And to do that, we're going to have an adder, which adds 4. Then finally, it needs to load the instruction at the address specified by the program counter, and we're going to do that by loading from a special instruction memory. So here's our setup that we have. Now inside the instruction memory, we're going to store all of our instructions, just like we saw when we were talking about the ISA. So if you go back to the lectures we had for the ISA, you can see how similar this is to what we had before. We have a memory and a program counter, and the program counter loads from the memory. If we walk through an example here, say the program counter is equal to 4, we can see what happens. So the program counter outputs 4. This goes into the instruction memory. That loads the instruction at address 4. Now this program counter also goes into the adder, where we add 4 to it, calculate the next program counter value, which is 8, and then this goes around back to the PC. And then when the clock comes along, the PC will be updated to be 8 for the next instruction. So you'll note here that we have a separate instruction memory. When we talked about the ISA, we talked about how there's only one memory for instruction and data, but when we talk about designing the processor, we're going to start out with separate instruction and data memories to simplify the design. When we get into pipelining and caches, we'll talk about how you can have just one memory. So we talked about instruction fetch. Now let's talk about ALU operations, in particular R format instructions. So what do they do? Well, the first thing they're going to do is read data from the register file. Remember, these instructions specify RS and RT. Those are the two source registers for the operation. So here are our inputs. These are the addresses of those registers. It specifies which registers to read. And then we have two outputs. This is where the data comes out from those registers. So we can read out the values from those registers. Then we need to do the ALU operation. So obviously to do the ALU operation, we need an ALU. And if you look at the ALU, it has another input here, which is the ALU operation. This is what specifies what the ALU is going to do. Is it doing addition, subtraction, and etc.? Finally, we need to be able to write the data back into the register file. Remember, R format instructions specify an RD register, which is the destination, or the data is written. So we need to be able to specify that into the register file, and then we need to take the data out of the ALU and write it into the register file. So this looks very similar to what we had in the ISA lecture. There we had a register file with two outputs going into the ALU and then writing back into the register file. So again, this should be very familiar. So here's a question. How many bits is the data here for write data? Is this input a 5-bit input, an 8-bit input, or a 32-bit input? So this is a 32-bit input. This is the data that we're going to write into the register file. This is the output from the ALU, and it's going to be a whole word. Remember, the register file stores data in 32-bit words, so this is the data we're writing in. Write register above it is only 5 bits because that's specifying which register file entry to use. And there are only 32 registers, so you need 5 bits to specify which register, but each register is 32 bits wide, so you need 32 bits of data to put into the register. So if we look at this here, we saw there's this ALU operation control. We also have another control here, reg write. This specifies if we're going to write data into the register file. So if there's a 1 here, the data that's on the write data input will write into the register, and if there's a 0, it won't write into the register. So here's a question. When would you ever not write into the register? Do you always write into the register file? Maybe on R format instructions or J format instructions. So an example of this is a J format instruction. If you're doing an unconditional jump, you don't calculate any results, so you don't write anything into the register file. There are also some I format instructions, such as if you're writing into the memory, you're doing a store, you don't write any data into the register file. So we don't always write into the register file, and that's why we need to be able to control it. So what do we have so far? We have instruction fetch with the program counter, the instruction memory, and its adder. And we have our ALU operation with a register file and an ALU. So what are we missing? Do we have everything? Are we missing something for doing comparisons, for example, for jump instructions? Are we missing a data memory? So what we're missing is a data memory. We can already do the comparisons for the branch equal and branch not equal by using the ALU and doing a subtraction. But what we don't have here is a way to load and store data from memory. So let's talk about that. Memory access. What do we do in memory access instructions? Well, we need to calculate the address, and we can do that using the ALU. Then we need to send the address to the memory, or if we're doing a write, we need to send the data as well. So our memory has an address input and a write data input. If we're doing a read, we then get results back. So we need a way to get the data out, and here's the data coming out of the memory. So if you look at what this memory has here, it has two control inputs, memory write and memory read. What would happen if we tried to read and write at the same time? Is this impossible? Would we corrupt data? Or is this not a problem because we have separate data inputs and outputs on our memory? So what would happen is the data would be corrupted or be invalid. Remember how memories work. So in a memory, you activate a whole row of the memory and then you either read or write the data. If we tried to read and write at the same time, the bits would get overwritten and it wouldn't be clear what we get. So here's another question that's actually somewhat more important. How do we calculate the address with an immediate value? So if we want to calculate this address, can we add the immediate and a register value using the ALU? Can we use the ALU to sign extend the immediate value? Or do we need to already sign extend the immediate value and then use the ALU to do the add? So what we need to do here is we need to sign extend the value somewhere else and then use the ALU to do the add. And the reason for this is we can't use the ALU for both the add and the sign extension. We need to have some extra logic. And so what we need is this bit over here, a sign extension logic, which takes in a 16-bit constant and sign extends it to 32 bits. Then we can use the ALU to do the final add.